Govind, what are we waiting for?
We are sharing the link, sir. It is going to students in the groups. Students are joining on YouTube and our Facebook page.
It's you here are people joining.
Yeah. Yes, a very warm morning and welcome everyone to our 20th weekend science session. With a gap, but with some more enthusiasm, we are back with one more eminent personality and very well-known scientist of our country who is responsible for all happenings of the premier National Institute, IUCAA Pune. Let's welcome the guest speaker, Professor Somak Raychaudhary, who will be exploring the facts and scientific zeal on the most popular topic amongst young scientists. Students in our Zoom room are the finalists of the project competition. We, the thinkers, are also eagerly waiting as we are going to declare the best 5 projects selected by the external panel from Pune through a virtual interview. I can see the virtual gathering of viewers on YouTube and Facebook. I also welcome the members of Astronomy Cell and Astro Club of Bajaj College of Science for this program. It's our pleasure to get the company of our trustee, Shri Sanjay Bhargav sir, for this program, and I invite Bhargav sir for a welcome address.
Namaskar. It's a beautiful morning here in Wardha, cold and fresh air. So we are very, very happy to have Professor Somak Raychaudhary with us. We're very privileged. We thank him for sharing his time with us. I'd just like to say 2 things. The first is that the only thing I think I can share with Professor Raychaudhary is he is an INLAC scholar, and I was almost an INLAC scholar. I was shortlisted, but no college would have me. The other connection that I can think of is between Calcutta and the Bajaj Science Center, which is that the Bajaj Science Center owes its origins to a generous donation by the Poddar family, Nana of Rahul Bajaj, and that is how Gandhi Gyan Mandir came into being. And from Gandhi Gyan Mandir's loins has come the Bajaj Science Center. So I would only remind you that we are torchbearers of legacies of our culture. And that is what the Science Center, in a way, is taking forward. We have to live in the modern world, but we must be very connected to our roots. So welcome once again, and we look forward to your lecture. I'll just, there is a gift we give to our people who talk, and it's a bust of Gandhiji. I will deliver it to you at Wardha, but please accept it from us. And I hand you back. Yeah.
Well, thank you very much, sir, for showing us the way towards the singularities in education in Wardha district. Now I am excited to tell you a few things about our today's speaker. Though his Wikipedia page tells most of the things about his achievements. Professor Somak Raychaudhary, born in Kolkata, is the director of Inter-University Center for Astronomy and Astrophysics, that is IUCAA, which is located at Pune. He graduated from Presidency College, University of Calcutta, with further studies at University of Oxford in UK. After his PhD from University of Cambridge in UK, he worked at Harvard Smithsonian Center for Astrophysics, which is in US, where he also was the part of the team that built the Chandra X-ray Observatory for NASA, which is now celebrating 20 years in space. After teaching for over a decade at University of Birmingham in UK, he returned to India as head of physics and dean of sciences at Presidency College, Kolkata, before he became director of IUCAA. Professor Raychaudhary is a fellow of National Academy of Sciences, Royal Astronomical Society, and the Astronomical Society of India. His research involves a wide range of topics in cosmology and astrophysics from the ground from space. He leads a substantial outreach program involving students from schools, colleges, teachers, and even the general public. He was one of the key people to start the Indian Astronomy Olympiad and selected as coach for the Indian Olympiad team to top results at International Astronomy Olympiad in 1999 and 2000. During his academic journey, he was mentored by the great physicist Professor Amal Raychaudhary in University of Kolkata, whose contribution led to this year's Nobel Prize, which is awarded to Roger Penrose from UK. Professor Somak also worked with 89 years old Penrose and his group. We would be delighted to know more about this association. With a great honor and pride, I invite Professor Somak to take us to the amazing world of black holes.
Thank you very
Yes,
much. So thank you and good morning. It's a wonderful morning here in Pune as well. Thank you everybody for coming on a Sunday. I'd like to share my presentation. Shall I start now with the sharing? Is that okay, Govind? Is my sound okay?
yes. So after the talk, there will be a question answer session for which the chat box in the YouTube will be enabled. Now we have disabled the chat box. So after your talk, we will enable the chats and we will collect all the questions from the viewers.
That sounds excellent. Okay, so again, welcome to black holes on a Sunday morning. I am going to talk about black holes in the context of this year's Nobel Prize. Of course, this is not the first time black holes have been rewarded the prize, and this will not be the last, because this not only is one of the major interesting subjects in physics now, it also leads to a lot of very fundamental questions that one addresses in physics right now. And over the last few years, in the Nobel Prize in Physics, we have seen astrophysical subjects being awarded more and more. And there is a reason for that. And that is because initially, when the Nobel Prizes started, about a century, more than a century ago, in the Nobel will of Alfred Nobel, which endowed the prize, it was said that it will be given for applicable sciences, applicable physics. And people thought that theoretical physics, mathematics, is not applicable. And so even Einstein was given the Nobel Prize for the photoelectric effect, explaining the not really the theory of relativity. But as time went on, people realized that it is impossible to separate theoretical physics and applicable physics, because a lot of things that come into physics through theory go into applicable physics straight away. I mean, so astrophysics was ignored as a theoretical science, as an esoteric science. But people realize that, if you think of the phone that you have in your pocket, almost every element in it has come from an astrophysical application. The digital camera was invented by astrophysicists. The MRI that you get when you go to a hospital came from basically an astrophysical problem, and things like that. And so slowly the scope of the Nobel Prize has now expanded to include all kinds of physics. And so this year's Nobel Prize was given to these three people. Roger Penrose got half the Nobel Prize, and the other two, the other half went to the other two for discovering a black hole and characterizing the black hole in the center of our galaxy, and Roger Penrose in general for black holes. Now let me introduce what a black hole is, and I understand that most of the people who are listening would be from high school and school students. So I'm going to go and introduce it at a very basic level. If there are people here who know a lot about black holes, might get impatient. So be patient, and I'm going to start all the way from Newton. But before that, I want to say black holes in general get a very bad press in film and in fiction. People think, oh, black holes are very dangerous. They come and suck you in, and they are after you. They want to get you. Actually, black holes are very, very friendly beings. They are if you don't go near them, and they're not near you, right? So they are not out to get you, okay? And at the end of today's talk, I'll be very happy if you go away with the impression that you don't need to wake up in the middle of the night and have nightmares about black holes. Okay, let's start from Newton. Well, this is something that everybody learns in school. Newton talked about what is gravity. As you know, during a pandemic like what happened this year, Newton's University of Cambridge was closed for more than a year during the plague, and they all had to go home. Newton went home to live with his aunt, and in a house where there was an orchard with apple trees. And you know the story about how Newton came to the idea of what gravity is, sitting there. It all happened because of a pandemic, and Newton got during that year Newton invented calculus, and Newton invented the binomial theorem, and also Newton found a way of explaining gravity. And his idea was that anything that has mass in the universe pulls each other through a force that is proportional to the mass of the objects and inversely proportional to the square of the distance between them, which means the further you go away from each other, the force drops. So this was his way of looking at gravity, and about for 200 years, we thought about gravity works this way. I will tell you how Einstein's view changed our looking at gravity. But this led to a very important concept, and that is the concept of escape velocity. So you are here on Earth, and the Earth is pulling you, and that is why you are standing on Earth, right? And so if you throw something up, it will come down, because the gravity of the Earth pulls it back. Unless you throw it at a certain velocity, which is called escape velocity, and then it won't come back anymore, it can escape from the Earth, right? This escape velocity is very high, and this is what, for example, people who design rockets are worried about, right? So you have to attain that velocity if you want to break free of the gravity of the Earth. And it's given by this very simple formula. It goes gm over r square root, and this m then is the mass of the Earth, and the r is the size, which means that the distance from the center of the Earth where you are standing. If you are somewhere up in space, then that r will be the distance from the center of the Earth to you. So black holes can be understood from this kind of a classical picture as well. So we know now, and Newton didn't know this, but we know now that nothing can travel faster than the speed of light. So if your escape velocity is higher than the speed of light, then nothing can escape from you, not even light, right? So this is a classical way of thinking about black holes. A black hole is an object from which nothing can escape. And so light cannot escape, and so it just means that the escape velocity is very high. So how can you make something that compact or that massive that nothing can escape from it? the escape velocity is very high. So let's think about this. So what is the escape velocity from the Earth? The escape velocity from the Earth is 11 kilometers per second or 43,000 kilometers per hour. So, I can't drive my car that fast. And, if I try to, the police will catch me first. So this is, and even ISRO can't launch a rocket that fast. We don't have the power to do that. It's a very, very high velocity. The way we launch rockets is that we take a rocket and take it to a high orbit and then launch it from there so that the R is much larger and so the escape velocity is much smaller. So escape velocity is pretty high. Similarly, but not as high as the speed of light, which, as you know, is 3 lakh kilometers per second, and I'm talking of 11 kilometers per second, right? From the sun, it is 600 kilometers per second, nowhere near the speed of light. Of course, that means that the planets cannot escape; they are trapped with the sun, right? So how can you make it so high that my dogs are getting excited out there? So how can you make the escape velocity so high such that it can exceed the speed of light? It just means that you can either increase the mass, keeping the radius the same, increase the mass. That is a very hard thing to do. The other way you can do this is that you keep the mass the same of the object and then shrink it down to a small r, because you see in that formula r is in the bottom, and so if you make r smaller, the escape velocity becomes larger and larger and larger, right? And so you can, in principle, make the escape velocity very high, higher than the speed of light. And this came as a concept. Even after Newton, people started talking about this. What happens if a star, they call them dark stars, what happens if a star is so small that nothing can escape from it? The escape velocity is very high, right? People like Laplace, people like the various contemporaries of Newton started thinking about this. But you can see the speed of light is very, very high. Now, if you look at how much you have to shrink something so that its escape velocity will become larger than the speed of light, it is called the Schwarzschild radius. And I'll explain where it came from in a minute. And that comes from this particular formula, which is very, very compact, very simple. It just tells you that if you have something of mass m, then 2gm over c squared, c is the speed of light, gives you a radius of the corresponding black hole. So if you have to shrink something to that size to make it into a black hole. So anything can be made into a black hole. You can be made into a black hole too, but I'll have to shrink you to that size. So for the Earth, that size is less than 1 centimeter. So if you shrink the Earth to something that is less than a centimeter, and I don't know how you can do it, then you can make the Earth into a black hole. If you shrink the sun to something that is less than 3 kilometers, 2.95, you can make it into a black hole. The sun will never become a black hole, right? But there are ways other stars can become a black hole. So that's the whole thing. You have to find a process to shrink things to that size. So Newton so to do that, you cannot depend on Newtonian way of looking at gravity, the thing we learned in school. And that is because when we are looking at things that are so dense and speeds, called the corresponding escape velocities, will become very close to the speed of light, Newton's laws do not work anymore. Newton's laws are a special case of a much larger theory of gravity, which was given to us by Einstein at the beginning of the 20th century. And Einstein actually realized that there is a fundamental flaw of looking at the way that Newton looked at gravity, which is it is a force between two objects, which is like it is connected by an invisible string. It's not like that. In fact, it is very difficult to describe gravity on very large scales with that kind of an idea. Actually, he then proposed another idea, which works for all cases, and it also works for the cases that Newton talked about, which is our scales in which we operate in the lab and on the Earth. And that's why Newton's laws work very well for us. And Einstein said, actually what is happening is that if something has mass, then it distorts space around it. So in Newton's theory, there was no space. The place in between objects like the Earth and the sun and the planets, that place is empty. It is vacuum. Einstein said, no, 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 there is something called space. In fact, he called it space-time because space and time are connected. It actually has a character. And what happens is, if you have something massive, then that space-time becomes distorted, and gravity, the force of gravity that you feel, is a result of you being trapped in that curved space-time, right? And I'll show you in a minute what that means. But Einstein said gravity is not really a force. You have to think about it in a different way. Now, that doesn't mean you stop reading what your teachers teach you in physics class in school, because actually Newton's formulation works absolutely fantastically in almost all cases, unless you're thinking about things like black holes and things like things that travel as fast as the speed of light. So later on, as you become a more advanced physicist, you'd have to learn the more general theory. So the idea is that space is curved around massive objects, and things move along space, along this curved space-time, and that is why even light curves along space, and even and things are trapped. So the picture is like this. See, you have the sun, imagine, and the space-time, which is given by that kind of green grid, has distorted around it. And here you can see the Earth, right? It also distorts space-time a little. But what is happening is that it is trapped in this curved space-time, and it is going around the sun because it is trapped there, not because the sun is pulling it by an invisible string. Okay, right. And so, and it is going around because it has angular momentum and it goes around. Otherwise, it would have fallen right in because the whole space-time is curved like that. Okay, because it has angular momentum in physics, angular momentum cannot be destroyed. So the Earth doesn't fall in, it goes around, but it is trapped in that. And all the planets are trapped in this curved space-time. Okay. So what happens when you shrink that object? Then this curve in space becomes more and more and more and more curved. So things can't climb out of it. And so the escape velocity is the velocity you need to climb out of that curve in space-time. And the more curved it becomes like a well, the more difficult it is to climb out of it. That is that picture that I want you to now imagine. Okay. So Einstein gave us this formulation in 1915 of how to think of gravity and how to apply this. The person who applied this to give us a formulation for what a black hole would look like and the size of a black hole is Carl Schwarzschild within a few months of Einstein publishing. Now, remember, 1915 was a time when the First World War was going on. Einstein wrote this paper in German in a German journal. It didn't come out to the English-speaking world because the English-speaking world, England and America, were fighting Germany in the First World War. So the English-speaking world did not know about this paper that had come out. And it actually came to India because Indians were not directly fighting in this war. They were fighting as allies of Britain. And Einstein's paper in German was first translated into English in Kolkata by two scientists called Satyendranath Bose and Meghnad Saha, who were just finished their PhD and had started teaching in Kolkata University. They both knew German very well. And they translated to English, and that translation went to England for English scientists to actually see the theory that Einstein had written, right? So that translation still exists in a book form. And so it went through India to the Western world, and Americans and the British first learned about relativity. Schwarzschild actually was a professor at Göttingen in Germany, and so he knew Einstein's paper, and he went to fight in the war for Germany in Russia, and he was killed in the war. But before that, while he was a soldier, he was solving equations in his notebook. See, this is what everybody needs to do. You need to do physics even when you are doing other things. And he actually solved while he was in the war fighting for Germany. And he wrote that solution down. He said, I found the size of a star in your formulation where it can be so compressed that even light cannot come out of it, right? And that is why we call it the Schwarzschild radius. And he wrote that in a postcard, sent it to Einstein. And then he died. So Einstein published that paper, and we still call it the size of a black hole, the size of the event horizon black hole after Schwarzschild. But still the question remained, how can you take a star and shrink it to a size such that nothing can escape from it, right? And that answer was given to us by Chandrasekhar. Chandrasekhar was a young student at that time, And he used to come and visit his uncle, C.V. Raman, in Calcutta. C.V. Raman used to, at that time, just before he got the Nobel Prize in 1930, he used to be at the Indian Institute for Cultivation of Science, and his nephew used to come and visit him from Madras. And he told him about quantum mechanics, he told him about astrophysics, and Chandrasekhar wanted to put quantum mechanics and astrophysics together. And he said, I'm going to go to the University of Cambridge. And he went there and worked under Paul Dirac, who was one of the founders of quantum mechanics. And he came up with this idea of how, as a star finishes its life of producing energy, when it finishes all the fuel as it produces energy, it has to collapse, and how the laws of quantum mechanics can stop that collapse and turn it into various kinds of objects as the star collapses. And that whole was worked out in the early 1930s by Subramanian Chandrasekhar, for which he got the Nobel Prize in 1984. So astrophysics takes a long time to get the Nobel Prize. So the idea for this black hole then is that then what will happen is that as a star collapses at the end of its life, if it is massive, so massive that even quantum mechanical forces can't stop it, then it will become a very small object, and much, much smaller than a few kilometers that I was talking about. And it will go inside the Schwarzschild radius. And what will happen around it is that space will become so curved that nothing can come out of it, not even light. That's the idea. So as I said, I would like to dispel these myths about black holes. They just go around and suck things in. Actually, what happens is that the black holes have a certain radius out to which they are effective in sucking things in, and they are not very much. For example, if the sun were turned into a black hole, it won't, because it is not massive enough to turn into a black hole. But if the sun were to turn into a black hole, the earth will still go around it, not knowing that the sun has gone into it. Of course we'll know, because there'll be no light, right? It'll be dark. But gravitation-wise, the effect of gravitation will be the same, right? In fact, nothing will fall into the sun, not even Mercury, no single planet, because the sun, if it turns into a black hole, its effect does not extend so far out even to the planets. So that's the way of thinking about it. Unless a black hole comes near your house and sucks you in, there is no way black holes are a danger to you. So Chandrasekhar told us that the end of star's life is such that if, for example, a star has a mass that is less than 1.4 times the mass of the sun, and our sun is less than 1.4 times the mass of the sun, then it will turn into something called a white dwarf, which is the size of the Earth, but the mass of the sun. And it will stop because of quantum mechanical forces stopping it. If it's slightly larger, between say 1.4 and maybe 3 times the mass of the sun, it will, its outer parts will explode into an explosion like this explosion that happened 1,000 years ago, the Crab supernova, and the middle part of it will implode to form something called a neutron star, which is about 10 kilometers across or so, right? That's a separate talk on stellar evolution. But if it's much more massive, more than 3 or 4 times the mass of the sun, nothing can stop it from collapsing, and it will collapse into a black hole. So the idea is that space-time will curve around it such that it's so deep that even light cannot come around out. And so it will have an event horizon given by that Schwarzschild radius, which means nothing can come out of inside that event horizon. Anything that is inside there, any matter, any light, cannot come out. And that is why it's called event horizon. You can't see anything like that from outside. And the black hole collapses to something called a singularity, which has been a difficult thing in physics for a long time, because what happens when it becomes so small that its density becomes infinite almost, apparently, right? Now, Roger Penrose and Stephen Hawking started working on this in the 1960s, 1970s. And the reason that Roger Penrose got the Nobel Prize and Stephen Hawking did not, because he's passed away, and Nobel Prizes are not given to people who have, after their death. Otherwise, this rewards the work of Hawking and Penrose together. And they showed that this collapse to a singularity comes naturally from the laws of physics. It is nothing unnatural. This is the reason. We still don't know what is inside the event horizon. We still have to find out. Penrose or Hawking have not told us that. But they found the mathematical formalism to show that naturally there are these singularities occur. The Big Bang from which the universe emerged is a singularity. The black hole is a singularity, and these things naturally come from the laws of physics. And what he did was he took Einstein's theory of relativity and showed in particular cases, this is like, for example, the collapse of a star, this naturally happens. And to do that, he had to use the results from this particular paper, as was mentioned before by Amal Kumar Raychaudhary. Amal Kumar Raychaudhary actually came up with a very general formulation of Einstein's theory of relativity, in which he incorporated many things like rotation, like shear, like all kinds of other physical effects to make it applicable to, for example, things like stars as they're collapsing, because the star doesn't collapse just like that. The star is also rotating. The star has tidal effects and things like that. And all that, this paper is mostly a paper on geometry, but it incorporates Einstein's thinking into how the geometry of space-time is curved by matter. And Hawking, Stephen Hawking, in his PhD thesis, used this formalism. He called it the Raychaudhary equation. The name comes from him. And then he got together with Penrose and showed that this is possible. In fact, when I first went to Oxford and I met Roger Penrose, he asked me whether I was related to Amal Kumar Raychaudhary. Because my surname is the same. And I said, no, of course, he was my teacher. Of course, Amal Kumar Raychaudhary was my teacher. In Presidency College, he was my head of department. In fact, all three people on this picture have been my teachers in some place or another. I took my first course on black holes from Stephen Hawking in Cambridge, and attended classes from by Penrose as well. So it's very, very interesting that they used Amal Raychaudhary's formalism in characterizing this. And so, as Martin Rees says, this is a very original way of looking at things. Of course, Penrose has done quite a lot of other things. In fact, here in IUCAA, just across the road from here, we have an auditorium named after Chandrasekhar, where the entire tiles are done by Penrose. In fact, he designed the tiles. It's called Penrose tiles. This is a very interesting mathematical concept in which irregular shaped tiles can fill space. And this is now used by solid state physicists and biophysicists to describe what is known as quasi-crystals, right? So Penrose has done quite a lot of very interesting things. And as Martin Rees says, if Hawking were alive, he would have got the Nobel Prize. So we know that there are maybe three types of black holes. So there are black holes that come from stars. As stars explode and collapse to form these objects, they have masses near the mass of the sun. Now, the most massive stars that we know of in our galaxy is about 100 times the mass of the sun. So stellar mass black holes will be less than that, right? And then at the center of each galaxy, there is a black hole that we know of that is more than 1 million times the mass of the sun. These are called supermassive black holes. And there might be black holes in between. Until about a month ago, we did not know of any black hole that is more massive than about 100 times the mass of the sun. We've now discovered one that is in between, and then it kind of tells us maybe stellar mass black holes lead to supermassive black holes. We don't know how supermassive black holes form because there are no stars that big, right? So that's still an unsolved problem. So this year's Nobel Prize, of course, half of the Nobel Prize was given for the supermassive black hole. This is why black holes cannot be detected. This is a close-up picture of a black hole. It's black. Nothing comes out of it, right? Not even light. We see things in the universe through light. Either things are reflected off. So, for example, you're seeing me because light is reflected off me, or they emit light. But a black hole cannot emit anything. It cannot reflect anything. So this is why, even when I was a student, Stephen Hawking used to say, nobody will ever find a black hole. In fact, he had some very high-profile bets with people about black holes will never be found. Of course, he lost those bets in the 1990s. So here we are. Let's look at the work for which the Nobel Prize this year was given. In the middle of our galaxy, there is a supermassive black hole. This is what our galaxy looks like. So here we are in a galaxy that looks very flat. And We are a planet around the sun, which is about 25,000 light years from the center of our galaxy, in the plane of the galaxy. And this is, of course, not a photograph. We can't take a photograph of our galaxy from inside. This is an artist's impression. The galaxy is very flat. And if you look from top, it is, you can see these spiral arms, and the center is here, and the sun, along with the planets, is offset from there. And we're looking at the rest of the universe from where we are in this galaxy. Now, in the middle, there is a supermassive black hole. And how can we find it? Now, to do that, you can't, of course, see the black hole, but you can look at the effects of the black hole by looking at the motion of things around that black hole. Like, for example, you can study the sun, you can measure the mass of the sun by looking at the motion of the planets around it. And from that, you can measure the mass of the sun, right? So you can do that if you can go very close to the black hole and look at the stars that are going around that black hole and try to find out its mass. But to do that, you can see that this part of the plane of the Milky Way is just full of dust. It's just full of dust. It's black, and light cannot come through it, normal light. Also, you have to go very close to that black hole, and so you have to do all kinds of things, very smart things to do that. And this is what the Nobel Prize is given for. The Nobel Prize is not given for just an idea. You have to actually make it work. So Milky Way from inside looks like this is a place. This is a picture of the Milky Way from Chile, and you can see that if you're looking, for example, from here towards the center of our galaxy, you will see that there's a lot of dust in there. This is a real picture, and the supermassive black hole is right there. So we have to go and see through all that dust. So how do you do that? Actually, there's a star cluster in the middle of our around that black hole. The black hole is marked here as Sagittarius A, and it's right down here. We can't see it, but there are clusters. There's a cluster of stars around it, and you have to measure the motions of them. But first, you have to. They're going around like that, right? So you have to look through the dust. And so these two people, Andrea Ghez and Reinhard Genzel, did this independently of each other. Andrea Ghez has a group at the University of California, Los Angeles. She used the Keck telescope, which is a telescope in Hawaii, the 10-meter telescope. One of the two telescopes are there, 10 meters each. And Reinhard Genzel used a very large telescope, BLT. There are 4 of them in the same building in Chile, in very near the telescope whose picture I showed you in northern Chile. So there are 2 independent experiments did the same thing. One of the things you have to do is you have to beat the effect of the atmosphere. You know, stars twinkle because light from outside the atmosphere comes through the atmosphere, comes to you, and the atmosphere itself is changing quite a lot because the air is moving, but also throughout the day and night, the atmosphere's temperature, pressure, density changes at every point. And so as the light comes in, the image that is formed moves around. And if you're taking a long exposure image, then it gets blurred. So in order to beat this effect, you have to do a smart thing called adaptive optics. So here is, for example, the Keck telescope that Andrea Ghez used. It looks like this. There are 2 of these telescopes, and the mirror looks like this. It's 72 segments, right, that make up the 10-meter primary mirror. And what we do, what they did, was that you can move each of these segments to change the shape of the mirror in real time, so that in anticipation of, because you know how the atmosphere is changing the image of the star from a small telescope nearby, and that is fed directly into a computer into the telescope. And what the telescope does then, in response to that, it changes the shape of the atmosphere to keep the focus very fine, right? It's called adaptive optics, and this is how it works. So you change all that. And here's an example of how it helps. For example, here's a picture of near the galactic center where all the stars are. And you can see without the adaptive optics, you wouldn't have been able to actually pick out the stars separately. But this is a picture in which you can see the stars separately around. The black hole is around there, which is black, which you can't see. But you can see the stars very clearly. And the second thing they did was they observed at 2 microns in the infrared. And in the infrared, the dust that you see in the plane of the galaxy becomes transparent and light passes through, right? So this is at 2.2 microns. they used infrared detectors, and they used a telescope in which the telescope itself can be modified in real time, faster than a second, so that you can actually see the detailed stars. And this is what they came up with, right? So here is from 1995 onwards, stars at the center of the Milky Way. Here is where the black hole is, that star-shaped object, which you can't see. But the others are real pictures of stars taken night after night after night. From 1995 onwards, this is Gez's work. Genzel started in 93. And for 25 years, they mapped the positions of these stars every day. And you can see the orbits of the stars around the black hole, which is there. And you can see this star, for example, S2, which is the yellow orbit. It goes around the black hole every 15 years. And they've been mapped, their entire orbits have been mapped, right? And if you map these orbits, you can find out what that thing in the center is that is making these stars move, right? This is absolutely beautiful work. And imagine the amount of work that has gone into this for the last 30 years, taking the positions of these stars every day, using this amazing big telescope that the entire telescope is modified to do this. And so the Genzel and Gez's group did this, and from each of these orbits of the stars, you can measure. You use Kepler's laws to measure the mass of this object out here. Kepler's laws tells you that, of course, the orbit is elliptical, and the mass was measured as 4 times 10 to the power 6, 4 million light years. So 4 million solar masses, the mass of that object. And the size of that object is very small too, because you can see that the star comes very close to that object. So if it were a cluster of stars, then it would be much, much larger than that. So it's a single object with that mass. And the only thing that can happen is a black hole. So they proved it's a black hole. Okay. Now, these are the supermassive black holes that exist. And so Gez and Genzel did the work on them. Let's look forward and see what else we can do with these black holes. We know that we have the stellar mass black holes. How do you see stellar mass black holes? Stellar mass black holes you can see in many ways, which of course in the 1980s Hawking said it's impossible, but we have now shown this to be true. How do you do that? Most stars in our galaxy are in binary systems, actually more than 50%. Stars are not alone. In fact, our sun is unusual because it is a lonely star. Actually, Jupiter failed to become a star. It could have become a star. But most stars, actually, then think about it. Most planets have 2 suns in the sky, like Tatooine. So think about 2 stars, and they're going around each other, okay? And but one star will be bigger than the other. So as the more massive stars evolve faster, they die faster, okay? So say the bigger star will evolve, it will finish its fuel, it will go supernova. It's a very massive star, so it becomes a black hole. Right? Now the other star is still evolving. It is still alive. It's still not alive in the sense, but it's still producing energy. But at one point it will then also start reducing its amount of energy, and it'll expand. Right? The first stage, it becomes a red giant, and its outer layers will be pulled less by the sun because it's become very big. And in fact, the black hole has a very strong gravity for things that are very nearby, as I said. And so it will start pulling the outer layers of the other star around it, and it will fall on that, on the black hole. Now, nothing can go straight into a black hole because it is angular momentum, as I said. So it will come and it will form a disk around it, a little disk. It's called an accretion disk. Now, this disk will stay around the black hole, and slowly that matter will fall in. But that disk sits around the black hole. It's outside the event horizon. And because of the gravitational potential energy of the black hole, it's extremely strong, the gravity, it becomes very hot. And that matter that is falling into the black hole can become almost 1 crore degrees hot, about 10 lakhs at least, right? So once something becomes 10 to the power 7 degrees hot, it starts emitting X-rays. So stellar mass black holes are best observed from the effect of the gas falling into the black hole, and it becomes, and it emits X-rays. So you need X-ray telescopes, right? So so this is an artist's impression of the matter that is going around the black hole, and it's glowing in X-rays. The problem is, so this is another picture of a black hole that came in the picture, came last year. This is a supermassive black hole, of course, but it was formed in a different way. So I'm just telling you, the problem is that it's emitting X-rays. Now, you know, in the electromagnetic spectrum, you have a lot of kinds of light. You have the normal light that we see with the eyes, and that's right in the middle. Andrea Ghez and Genzel, they used infrared light, which is slightly larger wavelength than normal light and lower energy. But these stellar mass black holes in binary systems, they are so hot, they emit really small wavelength light called X-rays. The problem is X-rays do not come through the atmosphere. The atmosphere blocks most light. You have a window here, the optical window, in which the light that we see comes in through the atmosphere. It's a coincidence, isn't it? For example, if our eyes saw only, say, infrared light or ultraviolet light, we would not know the stars are out there. So think about it. We can only see the light that comes through the atmosphere. But if we want to see X-rays, we cannot see it from the Earth. We need to take a telescope and send it into space. And this is why this kind of astronomy is so new. We only learned to go to space in the 1950s. So the Chandra X-ray mission, which you have heard mentioned, was built by NASA, named after Chandrasekhar, in the 1990s. And it was launched in 1999 to do just this, to look for black holes. That was its mission. And now in India, we have our own mission called AstroSat, which is up there for 5 years. We have an X-ray telescope in space, which ISRO has launched, which is finding black holes everywhere. But the Chandra X-ray mission, in which I was involved, as you heard, in the 1990s, was built such that this telescope has exquisite mirrors so that it can image these systems. And it is on a long orbit of 64 hours, so that it can go very far away from Earth. It goes 122,000 kilometers away from Earth. And it can observe away from the radiation belts that surround the Earth. Focusing X-rays is very difficult because you know that if you stand in front of X-rays, they go right through you. Normally, we have mirrors in which light falls on the normal, and they will go right through if they are X-rays. So to make X-ray mirrors is a very hard thing. We did this for AstroSat at the Tata Institute, where there are mirror labs. The first time this was done was for Chandra in the institute I worked at Harvard-Smithsonian, where the thing is you have these rays coming at grazing incidents. If you go like this, it will go right through. But if you actually have something come onto the mirror at a very small angle, then it doesn't go right through. It gets reflected off the surface, and then you can build long mirrors such that X-rays that come in are slowly nudged to and this is why a camera, and this is why you can see the telescope is about 5 meters long, and X-rays come through here, and they are focused onto the cameras which are there. Okay, so I'll show you an example of what kind of observations you can do with this to look for these things. Here, it's from my own work of observation of Centaurus A. Here's Centaurus A, which is a nearby galaxy in which there's a supermassive black hole in the middle, 1 billion times the mass of the sun. But it also has lots and lots of stars, binary stars, which have black holes in them. This is a picture which is taken by a normal telescope on Earth. This is optical telescope. So everything that you can see in here, all the light comes from normal stars, which are a few thousand degrees hot. And so they're emitting rays, optical rays that you can see with your eyes, right? You take the Chandra X-ray telescope and point at it for about 1 million seconds like we did, and there you are. This is an X-ray picture of on the same scale. What can you see? You can see the gas falling into the supermassive black hole in the middle, and as a result being ejected in the form of a jet, as a vomit almost, and that is traveling close to the speed of light across the galaxy. But all these little things that you can see are X-ray binary stars, the accretion disks around compact objects. Many of them are neutron stars. but many of them are black holes. In fact, I had a PhD student who did his entire PhD on all the objects that you see in this picture and modeled every single of them and found that at least 5 of them he could prove to be black holes. And you don't see the black hole, you see like this. You don't see the black hole, but you see the accretion disk around it, and it is pulling in matter from the nearby stars. Yeah. So in this particular picture, you have both supermassive black holes and stellar mass black holes. So this is the way you find both types of black holes. Govinda, can I take 5 more minutes because I want to look at the look forward to what we are going to do next. Is that all right?
Yes, sir. Yes, sir. We have enough time.
So let's look at what now is there in black hole physics, particularly for India, because now we've got into the game. We led the field in the theory of gravitation, and now with Astrosat we can already find these black holes that are in emitting X-rays, and these black holes are found in the middle of galaxies and spread all around the galaxy. Till now, for the smallest black hole we know is about 3.8 times the mass of the sun from Chandra, and it's about 17,000 light years away. The nearest black hole that we have found is 1,600 light years away, so you're safe. It's not coming to you. Don't worry, right? But now we're going to see what else we can do. So in India, we are now getting into these very big global projects. They're called mega science projects. In India, we worked in small institutes all over the place, but now we are a major player internationally. And the Indian government, in particular, the DAE and the DST, are putting in a lot of money for India to join. As you know, we've joined CERN last year, the premier institute for particle physics. The first 3 of these are astronomical objects, and all have amazing links with black holes. And I'm going to talk about the first 2 very briefly, just to show what is going to be available to you who are students in schools and colleges now. When I was a student in school and college, I did not think India will have facilities, international facilities, to do this kind of physics ever. And that is why I went abroad to study. I don't think you will have to go abroad to study astrophysics, because we here in India will have a lot of, and with Indian facilities, a lot of this stuff. Actually, India is a partner in building one of the largest telescopes in the world, the 30-meter telescope in Hawaii, and I'll talk about that, and then I'll talk about LIGO. 30-meter telescope, which will be built in Hawaii possibly, probably in about 2031-32, is a very large version of Keck. So I showed you the Keck telescope is a 10-meter telescope with 72 mirrors. This is a 30-meter telescope with 492 mirrors. Same design, same way you can change the shape of the mirror to increase resolution. And 5 countries are building it. Andrea Ghez actually is one of the people who's driving this, and I sit on various committee meetings with her because I represent India in these meetings. In India, about 10% of the telescope will be built by India. And it's not that India is giving people money. In China, Japan, Canada, and some of the US universities, we are going to build this. Of those 400 mirrors, 100 of those mirrors will be actually polished and configured in India, in Bangalore, at the Indian Institute of Astrophysics. The assembly of under each mirror segment, 490 mirror segments, that drives the mirror segment is actually they're all being built in India. And Indian engineers will have to build it. So if you're an engineering student now, you can get involved in all this, because this is a major engineering problem. It is not a physics problem anymore, right? And the entire software is actually being written in Pune that will drive this whole telescope by 3 companies, right? So all this is happening here. And this will find not only a lot of other stars near the center of our galaxy and characterize the black hole much better, but it'll find these supermassive black holes in the middle of a lot of galaxies around us. And this is why Andrea, for example, is interested. And then finally, I come to gravitational waves, which is our key to studying black holes. As you know, this was a different Nobel Prize from 3 years ago. And the gravitational waves were discovered. And in the discovery paper, out of 1,000 authors, 40 were from India. And right now, we are one of the leading nations in the world in gravitational wave science. Why is that? What is it? Einstein predicted that, as massive objects in space-time curve space, but if something moves in space-time, it will create ripples. Just like a duck moving on a pond creates little waves and ripples. Things will, so for example, take the most extreme thing, two black holes, and they're going around each other, and they're merging to form one black hole. That will create a lot of ripples in space. And the space itself is going to vibrate. And this is called gravitational wave. But Einstein wrote a paper in 1916 saying there's no way you can actually detect them because the amplitude of these waves is going to be so small, it's less than the size of the nucleus of an atom. So nobody's going to, and that was detected in 2015, two black holes merging 5 years ago. Until then, we have 56 such detections till now. So how small is this? You can see that if you think of human hair, it is about 100 microns. And the atomic diameter is 10 to the power minus 10 meters. The gravitational waves has a displacement of 10 to the power minus 18 meters in the gravitational wave detectors that are used now. And that is so small. And you can do that through a process that I'm not going to describe now called interferometry. And these things actually have laser lights bouncing off mirrors within a 4 kilometer by 4 kilometer L-shaped object. It looks like this. And it's a Michelson interferometer. And these tubes, which are 4 kilometers long, have the highest vacuum in the world. So you need vacuum technology, you need laser technology, you need the most advanced ways of isolating vibration from everywhere. Because if you're measuring vibrations of 10 to the minus 18 meters, then you need to, for example, if you go and jump around it, you can detect those vibrations. In fact, when the first gravitational wave was detected from these two places in America, Hanford and Livingston, which are 3,000 kilometers across, we were worrying whether we have detected a thunderstorm in Nairobi in Kenya, because it detects any such vibration anywhere in the world, right? And because we know what thunderstorms look like, we can isolate them, okay? So any train going anywhere in India can be detected by a gravitational wave telescope in India, right? So that's the challenge. It's very, very sensitive, the most sensitive instrument in the world. The detection 5 years ago looked like this. The whole thing lasted 1/5 of a second. And this is how space vibrated during that time, right? And it was detected independently in both of these places, okay? And it came from two black holes that were about 30 kilometers in 30 solar masses in size. And actually, the Schwarzschild radius is the size roughly of Karnataka and one of the Indian states. This is one of my students drew this picture for a popular article. I think it's very nice. And they merged together to form something that's 60 times the mass of the sun, which is roughly the size of half of Maharashtra, right? That's the size, the event horizon of that black hole. Think about it this way, okay? So now we have found all these things from the gravitational wave detections. We've found that, and each gravitational wave detection gives us 3 black holes. 2 black holes merge to form a bigger black hole. Here, if you look carefully, the figure that is given on the y-axis is the mass of the black hole times the mass of the sun. So you can see the purple things are all the black holes that are found from X-rays, from Chandra and now AstroSat and things like that, okay? These purple ones. But the blue ones are the ones, the 3 black holes at each time found from the LIGO experiment so far. And the most massive one we found is 145 times the mass of the sun. So we are going into this gray area between massive, supermassive black holes and stellar mass black holes now already. And this gives us new ideas of how massive black holes can be. And you can also see how massive these things that have now been discovered by LIGO. Why am I telling you all this? Because we are building the 3rd LIGO, right? Not far from you, actually. This is going to be in Hingoli, not far from Nanded. And this will, we've already started building it. And together with the US, who have the 2 LIGO observatories, and the third one they will build here. And the reason they want to build a third one, and we want to build a third one, is that LIGO detectors are like microphones. They detect sound, but they don't know where it's coming from. So if you have three microphones, you can figure out by triangulating where these are coming from. And to have something very far away from America will mean that we can localize things very well and figure out which galaxy it is coming from. Right now, it is very hard to know that. And so we're going to build this. This is actually a picture drawn by our architects of what it will look like in Hingoli. This is what it looks like now. We've bought the land, and it's empty, right? This is the place where those two arms are going to meet, and that is marked now. And we have a fence around the place. That's all we have now. And we're going to build there slowly. By the time the students who are attending this meeting will become professional scientists, this will be built by 2027. We hope we will make it. So on social media, we are there. Follow us and look at what's happening. I leave you with some books that you might read to find out more about black holes. Einstein's biographies are very interesting. Kip Thorne, who got the Nobel Prize for gravitational waves, wrote this fantastic book on black holes and time warps. And then, if you are interested in time travel and wormholes and white holes and whatnot, you can read Richard Gott's book. I'll stop there. Thank you. Thanks, Govinda. I'm done.
Well, thank you. Thank you very much, sir, for explaining the concepts related to black holes in a very lucid manner. And we are delighted to know about the happenings in our country. That was the most important part for all of us. I'm sure you must have sensitized all the viewers. They must be ready with their questions. I invite your questions in the chat box now. All can text their queries, questions related to the talk in the chat box on YouTube. In between, we would like you to declare the names of the selected projects of our competition, We the Thinkers. For this, I invite Mr. Ariman Kejriwal, who has coordinated this event from Mumbai. Yes, Ariman, over to you.
Hi, everyone. Good morning. I'm sure you're all very, very excited to hear the results of We the Thinkers, which was an online competition that was organized by the Bajaj Science Center in Wardha. I'd like to start off by introducing the competition and telling you all exactly what the students did. So in July, the Bajaj Science Center released a notice that informed students of the competition. Since then, students have worked tirelessly to research on a topic that they believe will benefit humanity. So we had a total of 150 students who submitted ideas in the form of PowerPoint presentations in August. The Bajaj Science Center selected 26 of these ideas. So the students worked with mentors and parents to further their projects. Out of these 26 students, 22 students submitted project reports and promotional videos. Professor Sujata Bhargav, former head of the Department of Botany at the University of Pune and a mentor of the Bajaj Science Center. Dr. Tushar Tamhane, renowned educationalist from Indore. And Dr. Vasudha Vanmali, former vice principal of the Janki Devi Bajaj College of Sciences, selected 11 out of these projects to be presented before a panel of judges. So in November, these 11 students presented their topics in front of a panel of judges. Our judges included Dr. Pankaj Potar, a scientist in the Physical and Materials Chemistry Department at the National Chemical Laboratory in Pune, Dr. Dhanashri Paranjpe, an ecologist with many publications in top international journals, and Mr. Kedar Champekar, a freelance ecologist, environmentalist, and educator. The students also promoted their work online on platforms such as YouTube. Some of our students' projects got over 2,000 views in the span of just a week. The students acted as true ambassadors for the Science Center. I would like to thank Dr. Podar, Dr. Pranjpe, Mr. Kedar, Bhargav ma'am, Dr. Tamane, Dr. Vanmali, Dr. Lakhotia, and all of the faculty at the Bajaj Science Center for taking out so much of their time to make this endeavor possible. And now, for the moment that all of you have been waiting for, we'll be announcing the top 5 projects of We the Thinkers. The panel has selected the top 5 projects, which will now be announced in no specific order. So it'll be in random order. We haven't rated it in accordance with merit. There will be 2 projects from Group A, which is the 6th and 7th graders, and 3 projects from Group B, which is the 8th and 9th graders. I would like to ask Professor Raychaudhary to announce the first top project.
Okay, great, thanks. Oh, congratulations for everybody. And actually, congratulations to everybody who participated in this. This sounds like a wonderful endeavor. And I'm sure there was a real competition at the top. And of the people who were shortlisted, I'm sure all the projects are very, very close together. Now, I've been given this list to announce, and the first name on it is Akshara Arvind Banjari, on kitchen waste to kitchen garden.
So Akshara's project was titled Kitchen Waste to Kitchen Garden. What Akshara did was she studied kitchen wastes and how they could be used and composted to produce kitchen gardens. Congratulations, Akshara.
Go ahead and tell us. Here you are.
Dr. Raychaudhary, would you like to announce the second name?
Okay, shall I announce the next one? Okay, yep. Next one on my list is Arnavi Amol Singham.
So Arnavi presented her project on Corona warriors exhausted in heat wearing a protective sheet. Now beat the heat with a nice cool PPE kit. So Arnavi's project was based around improving the conditions for nurses and doctors who are fighting the coronavirus. She introduced a certain fold or pocket that reduced the temperature inside these PPE systems to help nurses better endure the heat. Congratulations, Arnavi.
Thank you, sir.
That's wonderful. Both Akshara and Arnavi are in 7th. Now, the next one is from class 8, Mayank Mahendra Bhate.
So Mayank's project was titled Using Liquid Manure in Nurseries to Reduce the Mortality of Forest Plantations. Mayank's work included testing liquid manure and using control samples to see whether these liquid manures would be more effective than the conventionally used manures. Congratulations, Mayank.
Congratulations.
Thank you.
Wonderful. The next one on my list is class 9, Vanshika Sandesh Agrawal. Vanshika?
So Vanshika's project was based on trapping carbon dioxide. She looked at different methods by which carbon dioxide from the atmosphere could be trapped and then used for the production of certain goods and items. Congratulations, Vanshika.
Thank you, sir.
And the 5th name on my list is Anjali Mishra, also from 9th. Wonderful.
So Anjali's project was based on saving our earth from plastic. She was basically looking into the dangers that plastic posed to the earth and how we can prevent pollution. Congratulations, Anjali.
Well done.
So I'd like to congratulate all of our participants once again. All the 22 students who submitted their videos and action reports will be eligible for a book prize. But congratulations to all 150 students, and thank you so much for participating in We the Thinkers.
Great. Congratulations to everybody.
Well, thank you, Hariman. Thank you for your interest at Bajaj Science Center. We are happy with your kind association. You also toiled hard for this competition. Thank you very much. Now we are ready with our questions. So few questions. Sir, first question. Can a black hole be a type of wormhole for transportation to a parallel world?
Yeah, so interesting. I get this question a lot, and this also comes from science fiction, really. A lot of science fiction imagines black holes to be, because of the singularity, one can think of a place where space and time is violated to some extent. And so people have imagined in fiction, it's actually not possible, at least with current understanding of science. But people have imagined such that, because these are defects in space-time, maybe you can go inside a black hole and come out of another place in space-time. And then, you can time travel through it. And the connection would be called a wormhole. Now, that's why I flashed Richard Gott's book. If you can get hold of it, you can get it on the internet and also in print. It actually explains the science behind it. The problem is, if you fall into a black hole, you're not going to be yourself anymore, right? In fact, something that falls into a black hole will get ripped. All your cells and all your atoms and all your particles will get ripped into individual particles because the black hole has immense gravity, right? So how are you going to get the spacecraft into a black hole and out there again? First of all, you go into a black hole, you can't come out. There might be a quantum fluctuation that will spit you out somewhere else in space-time, but you can predict. You can't predict where you're going to go. And in any case, you're not going to be yourself. You're going to be your protons and neutrons and quarks by the time you go inside the black hole. So no, it is not possible to time travel through black holes only conceptually, because nothing can come out of the black hole, right? So there are thought experiments, theoretical experiments that people have been doing is you put a message inside a black hole, can it come out somewhere else in the universe? And whether that is possible or not. And even that is something that is a heavy subject of research right now.
Yeah, next question is, please tell us what is the length of black hole?
Yeah, so I already did that in my talk, right? So I talked about the size of a black hole. I gave you a formula, which is 2gm over c squared. If the mass of the black hole is m and c is the speed of light, that is the size, that's the radius of a black hole. And that just tells you this around the black hole, the size from which no information can come out, nothing can come out, no light can come out, etc. So that is the size of a black hole.
Yes. Next question. How neutron star can become black holes, as I have heard that it cannot be further compressed?
Yeah. So neutron stars happen when a star collapses, a remnant of a star at the end of its life, it's collapsing. And as I said, certain quantum mechanical forces can stop it. Now, this collapse. And depends on whether the collapse, which is due to gravity, is strong enough to overcome the quantum mechanical forces. The quantum mechanical forces come from the fact that they say that the particles themselves can't come closer than a certain amount, but it can if it's pressed by immense gravity. So neutron stars are a state in which they are, as I said, 10 kilometers across, the size of, say, a city, and but the entire mass of the sun or the star is in it. Now, sorry. Now it cannot go any further unless some more mass falls onto it. So I told you most stars are in binary systems. So say a neutron star is in a binary system with another star, and it is attracting, and the other star starts becoming very large and actually explodes, becomes a supernova. Then the mass that comes out of the other star, the neutron star is going to pull onto its surface, right? And as it falls onto its surface, then the mass increases. And as the mass increases, then the gravity of that resulting object can be larger than the force that's holding the neutron star. This is what happens, for example, in what is known as gamma ray bursts. This is one of the ways you can produce them. Another way you can turn neutron star into a black hole is the process that I showed you for the LIGO experiments. You can have a neutron star and another neutron star or another white dwarf or something like that collide and merge, and the resultant star will be much larger than the neutron star. And we found two such objects till now. We found two objects from which gravitational waves have been found that are neutron star and neutron star merge together to form a black hole. Actually, we found another one, which is a neutron star and a black hole merged to form a black hole. Now, it is interesting. I'll tell you another thing. All the gold that you have seen and platinum, we have a lot of gold bangles, actually gold jewelry. People, every single atom of gold that you have seen was formed in the collision of two neutron stars somewhere in the galaxy, because that's the only way you can produce gold. So what happens is that two neutron stars merge, become a black hole, but they explode before that. The outer shells explode, and in this merger, it is such a high energy merger, then atoms of iron and other things turn into gold and platinum, and then they're distributed in the galaxy. It's very, very interesting. We're only learning all this now. We've learned this only in the last 10 years. So neutron stars can turn into black holes, but they produce fantastic effects, fantastic fireworks in the process. And this is something that your generation is going to come up with, trying to understand how this works.
Yes, sir. Next question is from UG student. Why and how do supermassive black holes form only in the center of galaxies?
Very,
Were
very.
were they formed after the death of very massive stars during the early universe, or formed with formation of galaxy?
We don't know. It's a very, very interesting question, and it's an active area of research. There, astronomers have different views on them. First of all, you know that it cannot come from a star because there are no stars that are that massive. Now, we are learning that neutron stars and black holes merge to form more massive black holes. We are seeing them in the LIGO detections. Now, it could be that you start from small black holes and they merge to form bigger black holes merge to form bigger, and etc., etc. So you can go from stellar mass black holes to supermassive black holes. Now, the question is has there been enough time in the universe to do it? Is the universe old enough for small stars to merge to become such large things? In any case, where are they most likely to happen? Where the density of stars is the largest, and that is at the center of the galaxy, right? So, center of the galaxy is the place where such things can form. So, this is one theory, and nobody has worked out yet satisfactorily whether this is possible or not. The other way of doing it is, as you said, when the universe was very young and the universe itself was very small, when the first stars formed, they were probably more massive than the stars that are there now. And there is a theory that there are certain black holes that formed then, which are called primordial black holes, which we haven't found yet. But there's a theory that these primordial black holes that were formed when the universe was very small, that would have been very, very massive, right? So it could be that galaxies formed around these black holes rather than they forming in the black hole galaxies after they are formed. So all this is open question now, right? And this is what I'm expecting future students to do their PhD theses on, to find out how these things happen, how these things came to be.
Yes. Next question is from 7th standard student. How much time is required for merging two black holes?
So it depends on a lot of things. It depends on how massive the black holes are, how close they are, how fast they are spinning, and things like that. So, for example, the first gravitational wave event I showed you that was discovered in September 2015, that whole merger from our discovery till it merged took 1/5 of a second, right? Now, that depends on where you start. I mean, you can start from when the two black holes met each other and they went into orbit, and then they slowly sped up and stuff like that and merged. But we detected the gravitational waves from a time, so it's a matter of seconds. But then there have been other events which have lasted minutes, right? Now, so it depends on a lot of things, but it's a question of when do you think it started? When the black holes went into orbit around each other, and then slowly they lost energy and came closer and closer and closer. That could take many years. That could take thousands of years. So the whole process can take a long time, but the final moment when they merge can take very small time, a few seconds. Right.
Yeah. Students want to know about Hawking radiations of black holes.
Okay. So this is a question I get all the time. See, Hawking came up with a very interesting idea that we say that nothing can come out of a black hole. But he came up with an idea, and it was so fantastic that he actually published this in a newspaper first, then in a scientific paper. In fact, an article in Scientific American, where he said, what if, see, quantum mechanics tells us that out of vacuum, a particle and an antiparticle are created, and then they annihilate to form energy. Out of energy, a particle and antiparticle are created. So what if such a pair of antiparticle and particle forms very close to a black hole, such that as soon as they form, one of them goes inside the event horizon of the black hole. So what will we see? We will see one particle, and it is coming out of the black hole. We don't know about the one that went in there, right? So in such a quantum mechanical fluctuation, such things can happen when one particle can be created and you can think it is taking out some energy from the black hole and coming out of the black hole. So this is a phenomenon that is possible theoretically. And this is a way in which you can see some energy can come out of a black hole. The problem is that this is a very slow process. It will, something that comes out of the black hole can take away some mass from the black hole and it takes out this energy. And you can think of that a black hole can finally be destroyed by losing mass in this way, by losing energy in this way. Finally, it could shrink to zero. If you work out how long that takes for a stellar mass black hole, it's 10 to the power 60 years, 60. And the universe is only 10 to the power 10 years old right now. It's a very slow process. It's theoretically possible again, like wormholes. But actually, people have now started thinking, what will the supermassive black holes, if they emit Hawking radiation, whether it will be detected or not? And people have started to think about trying to detect such things. Maybe in another 20, 30 years, we'll come up with technology to actually detect these things from very massive black holes.
So if not vacuum, what is the composition then?
No, it's the two, it's energy, right? Photons split into two particles, right? And then they annihilate. So one of these particles can come out of a black hole, and that will have some energy. So quantum mechanics tells you that in vacuum, whatever, in vacuum, you can either create two particles, or a photon can split to become two particles, and then they annihilate again. All the time, this is happening. It's happening in vacuum. Also, it's happening for photons and particles. So Hawking radiation can happen from one of these fluctuations. If, for example, the black hole traps one of these particles of the pair that is formed.
Two more questions. How do black holes produce their enormous jets of hot, fast matters? 10th standard student wants to know.
Can you repeat the question again? I didn't quite understand.
How do black holes produce their enormous jets of hot, fast matter?
Right. So I showed you the jets. What happens is that as matter falls onto a black hole, as I said, it cannot go straight in for two reasons. One is, of course, the matter that's falling in will have some angular momentum, so it has to lose the angular momentum. So it rotates in a disk around the black hole. Secondly, all black holes have a maximum capacity as to how much it can take in. And it is because of this following very interesting reason. If something falls into a black hole, as it's falling in, it gets very hot and it gets very energetic. So because of the gravitational pull of the black hole. And so radiation comes out. As things are falling in, it produces energy. And that radiation actually stops the thing from falling in. It regulates the motion, right? And this is called the Eddington limit, the limit to which how much a black hole can take in every second. And that is because as things are falling in, it produces energy, and that counters the thing that is falling in. So in many cases of black holes, a lot of matter that is falling in at a rate that is larger than what the black hole can eat, right? So it ejects the excess matter in the form of a jet. And this jet, because the jet is this matter that is very near a black hole, is actually already separated in the individual particles. The protons and neutrons and electrons are all separated. It's a plasma. If they are charged particles, they follow the magnetic field around the black hole in the galaxy, and then go along the magnetic lines of force. Because they are charged particles, they follow magnetic field. And so they come out very collimated. We don't fully understand why things are so collimated, so narrow, but they come out in the form of jets, and they can, because they come out at very high speed, they can attain velocities very close to the speed of light. So this is it. This is a special kind of vomit though, because when I vomit, if you try to feed me a lot and I can't eat so much, I will also vomit, but I will vomit things that have gone into me. A black hole cannot vomit something that has gone inside a black hole. Here is the jet is coming from outside the black hole, because already as the matter is falling in, it is being prevented from falling in. And so it is ejected from outside the black hole. That's what jets are.
We'll take one more question. It's from UG student. Can we assume that black holes are stationary? If not, then are there any rogue black holes, or all black holes are at the center of galaxies only?
No. I mean, only supermassive black holes are the center of galaxies, right? And galaxies are moving. Galaxies are crashing into each other. So we have actually seen two supermassive black holes merging into one because the two galaxies merged. So, and black holes in the other black holes that are in the galaxy are always moving, because all stars are moving in the galaxy. So no black hole is stationary, right? The one at the center of the galaxy is almost stationary with respect to the galaxy, but the galaxy itself is moving. Okay, so the black hole is moving with it. But there are black holes in the middle of a galaxy where we've seen them move in the center of the galaxy a little. Yeah, because of, for example, it crashed with something recently. So nothing in the universe is stationary.
Well, thank you very much, sir. There are many questions. I will mail those questions to you in case.
Yes, of course. Yes, thank you.
And we'll post the answers of those questions on our, maybe on website or on our Facebook page, so that everyone will come to know about those questions. Now I request Sanjay sir to please sum up this session with your words.
You're giving me a task which I'm not equipped to do. There's only one question which Professor Raychaudhary hinted, that one of the unintended byproducts of this work on black holes was leading to some things which are affecting, or technological developments that have come about. Would you like to say something about that?
A lot of it. I mean, for example, I gave you the example of, let's take the modern things. There are lots of things that came from, for example, the space telescopes that have been sent up. A lot of the things that have been developed for them are now in common use. One example I gave was of the digital camera that we use, everybody uses in our phone. That digital camera was built for the Hubble Space Telescope that went up. And we knew that we couldn't send a camera up when the film came back, we'll develop it, right? So the digital camera was set up, and that itself has got a Nobel Prize, the CCD itself. Similarly, right now, and the Hubble Space Telescope, of course, has discovered lots and lots of black holes and associated systems. But think about the things that we are doing now. Just take the example of the LIGO experiment, where we are trying to detect these gravitational waves from black holes. In order to do that, we have to break the limits of technology everywhere. I'll give you one example. What you're doing is you are trying to minimize the vibrations so that we can detect these black holes. So everything that is inside these tubes I showed you have to be vibration free. The mirrors of which the lasers bounce have to be totally vibration free. So we've developed these suspensions so that outside whatever vibrations there can be, like trucks going or trains going or winds, etc., or earthquakes, the mirrors will be isolated. Now, we have a company in Glasgow who has developed this. The same people have developed a product for eye surgeons to isolate their hands as they do eye surgery, right? So that their finger does not vibrate if, for example, there is a vibration outside. Same thing just translates directly into a medical application straight away. And they're doing cataract surgeries and microsurgeries using exactly the same vibration isolation system. So that's just one example of hundreds I can give you.
So thank you very much for sparing your time. And one of the features of our education system is simply the lack of curiosity. And I think everybody is curious about the sky. As long as you can see the sky, in Vardha we can see the sky. In Pune you can't see much of the sky now. But I think it's one of the fundamental things which start the curiosity of kids. I think astrophysics, and I know that IUCAA has a very vibrant extension program where kids come in and spend time in a kind of center that you have there. So it's one of the, I think one of the fundamental byproducts of astrophysics is the nurturing of curiosity. And for that, we'll be all beholden to you. Thank you and good day.
Thank you very much.
Thank you, sir. On behalf of Bajaj Science Center team, I deeply appreciate your passion and devotion for building scientific temperament among students. Today's session must have encouraged students to develop their understanding in astronomy. We'll be waiting to meet you soon at our center in Vardha. Thank you very much for sparing your valuable time for our kids. Thank you once again, sir.
Thank you. It was a wonderful experience, and I would love to come and visit you very soon. Thank you very much. Bye.
Well, thank you very much, audience, for your kind patience and interest in our weekend series program. Two more sessions are lined up in series tomorrow and day after tomorrow. Follow our Facebook page for our outreach notifications. Tomorrow, join us virtually to witness amazing session on the conjunction of two planets. So with the words of gratitude towards Professor Somak, I declare the closing of this session. Thank you very much.